Chesil Beach is one of Europe's most famous and intensively researched geological features. It is dynamic, and its seaward profile is constantly changing. Storms and overtopping cause it to migrate almost imperceptibly eastward. Chesil Beach terminates at the mass of the island of Portland, where Chesil Cove has always been popular for swimming, diving and sunbathing. The beach forms a natural protection for the ancient village of Chesil, which nestles on the back of the massive shingle bank. However, through the centuries, every successive storm diminished that protection, eroding the bank and exposing the old houses to sometimes devastating sea flooding. In the late 1950s, the Portland Council embarked on bold and ambitious schemes to construct sea walls for coast protection and sea defence works to safeguard Chesil. I described the first two stages in a separate documentary video. It was all to be done in-house. Just south of the village was a high and extremely crumbly, friable cliff, which was being rapidly eroded by weather and by intense wave action at its base. A footpath and some cove cottages' houses were perilously close to that unstable cliff. Cliff falls were a danger to anyone on the beach. To deal with this, the council engineers designed a high mass concrete wave return wall, which was constructed during 1962. A deep trench was excavated for the foundation, which had to be in firm ground well below the beach level. The clerk of works for that stage was Percy Boutell, and my trainee colleague Mike Horton and I set out the wall for its construction. Here at the top in August 1962, I was overseeing the work with the clerk of works. This supported a wide promenade, extending the one built in the earlier stages of the Coast Protection Works up to the Cove House Inn. That Stage 3 seawall was completed in December 1962, and 60 years later it remains in excellent condition, having endured severe battering in numerous storms. Beyond, at its far end, the beach curves towards the rocky foreshore. Above this are the West Weirs, steep undulating slopes of Kimmeridge clay. Flooding was not the problem here, of course. A vast area of this coastal slope had for years been sliding downward towards the sea, and by the 1960s the movement was accelerating. That entire hillside was notoriously unstable, a situation that can be traced back to a massive landslide that occurred on Boxing Day 1858, when a vast area of Kimmeridge clay under the cliff moved en masse towards the beach. The land was left distorted into ridges, hillocks and valleys, and numerous cracks opened up in the ground. For possibly hundreds of years, surplus waste stone from the cliff-top quarries had been tipped onto the weirs. Those huge stone blocks imposed a cone weighing thousands of tons on the soft clay ground, which inevitably gave way. The sliding was lubricated by numerous natural water springs which riddled the area. At the lower edge, the 1858 landslide had pushed the corner of the pebble beach seaward, although within a few years the action of the sea had washed that loosened lobate away and the natural shingle shoreline had been restored. That clay hillside continued to move frequently over the next 100 years, but by the 1960s there was alarm that the landsliding was accelerating. On the hillside were several established recreational huts and an important footpath leading to Hallelujah Bay. The path had to be rebuilt by the council frequently due to the landslips. The instigator of the entire Chesil Coast Protection Works was the engineer and surveyor of the Portland Urban District Council at the time, Eric B. Cullen, whose deputy was Geoffrey King. To save money, wishing to avoid expensive consulting engineers, the council had decided that the entire scheme would be worked up and designed in-house. After studying and training, I was appointed Capital Works engineer, one of a very small technical team based in the council offices in Fortunes Well. These coast protection works were not big in the civil engineering scale of things, but they were challenging and complex, with changes and adaptations having to be made almost daily due to geological conditions. In 1963, under the engineer's guidance, having made a detailed survey of the area with my colleague Michael Horton, I produced the drawings and contract documents for this Stage 4 scheme. That year, 1963, the engineer reported to councillors on the urgency of the work. This is quoting, "In the last 3 or 4 years, since the scheme was first envisaged, the rate of erosion of West Weirs has accelerated, and the stability of the houses and the school to the east of the site could be in question, so that Stage 4 is now an immediate necessity. The problem is that the sea erodes the soft clay bank, forming a small cliff which soon collapses, causing the land behind to slide towards the sea. This process is now continually taking place. The works, which will be on clay foundations, will comprise a 10-foot 6 high mass concrete wall, similar in profile to the earlier stages, with reinforced concrete foundations. The foundations will form capping to steel sheet piling, 10 feet deep, laid on a 21-degree slope behind the mass concrete wall will be natural Portland stone grouted in concrete, with a 20-foot access path above and behind, the latter being on the same level as the previous stages. It continued, steps will be included at each end of this section to provide access to and from the beach. An essential part of the scheme is the drainage of the immediate area behind the wall, which will have to be carried out to stabilise the soft clay slopes already slipping, springs being piped and discharged to the beach. The work has been designed in accordance with information obtained from borehole reports and detailed site investigations by John Lang and Sons Limited in 1958 and by Dorset County Council in September 1962. My drawings were for a mass concrete sea wall curved on plan with a well-proven seaward-facing wave return profile, a vital aspect as the wall would have to dissipate of the powerful wave energy often experienced in the cove. On plan, the wall was effectively a huge horizontal arch which added great stability over and above the calculated stability of the individual components. In cross-section, the wall was designed to retain the steeply sloping land behind to stop it sliding. Calculations, including stability analysis to verify overturning moment and resistance to sliding and hydraulic pressure, all with a generous factor of safety. The 10-foot 6 high wall is on wide reinforced concrete foundations, the front of which forms a capping to a curtain of steel sheet piling driven well into the firm clay below the beach. In the 1960s, of course, we still worked in imperial measurements. Behind the wall is a 21-degree battered slope of natural Portland stone blocks bedded on imported stony fill and grouted in concrete, leading up to a wide promenade for access and amenity. This level prom is a major extension to that created in the earlier stages of the sea wall. An essential part of the scheme was the drainage of the hillside, to gather and pipe away the groundwater, which was a major cause of the landslides. The scheme had to be approved by a government ministry, so an inspector came in October 1963 to examine the proposals. He recommended some modifications, including strengthening the steps at each end to minimise the possibility of a breach occurring. He also suggested that the stop end wall should be of adequate strength and should extend as far as the dwarf wall behind the promenade. The inspector cautioned that the stability of clay slopes is notoriously difficult, so the regrading and land drainage design was critical. The changes were made and consent was duly given. Dorset County Council was concerned about the school close to the cliff top, so they appointed eminent consulting engineers, Gifford and Partners, to examine the scheme. They recommended further changes to bolster the structure, including additional interlocking steel pile counterforts at intervals extending to the back of the wall foundations. Counterforts counteract sliding and overturning forces by anchoring the wall deeper into the ground. The contract was duly let to A.E. Farr Limited of Westbury, Wilts, who, having undertaken major works in the nearby Portland Dockyard for the Navy, already had a local depot. Site huts, including my office, were positioned on the existing promenade, along with a large concrete batching plant and other equipment. Farr's agent was the highly experienced Dick Jones. Their quantity surveyor, Dick Richards, and the contractor's engineers were Vivian Hooper Greenhill and Roger Gosney. On site initially were 14 contractors' men, and the plant, including 22 RB and 19 RB cranes, draglines, a draught dozer and a Priestman excavator. The engineering drawings now had to be translated into physical work. The initial setting out was to establish the far southwestern end point, to which I set out a great chord line by theodolite across the beach. From this, a smooth curvature of the main wall was established by precise offsets at intervals. The end point was dictated by the terrain. It could not have been set further back without causing an unacceptably steep bank above. The end was to be among the rocky foreshore of huge rocks that had fallen from ancient landslips and from old quarry tipping. Behind the line of the wall, we marked out a grid over 100 feet to set the levels for the new regrading and revetment profiles. A temporary access road was made from the end of the existing promenade. A temporary land drain was laid alongside this road to help divert the spring water, and in mid-April 1964, some of the mass of clay which covered the beach in front of the wall was dug away. Excavation was now underway for the foundation of the mass concrete wall. Farrs then erected the frame for the piling. The main wall comprised individual bays of mass concrete, founded on a wide, reinforced concrete base slab. The front of the base was formed as a capping beam over a buried curtain of interlocking Larsen steel sheet piles, which were driven as deep as practicable into the underlying stiff clay. My works diary records that on the 24th of April, a large portion of the previous day's excavation had collapsed into the trench overnight and flooded, so we laid a further temporary land drain behind the working area. A few days later, a rough sea filled the excavation with water which had to be pumped out, and more of the bank had fallen in. The early stages of the scheme were dogged by the still moving bank, often covering the excavation and foundations. This had to be rigorously cleaned off before further concrete could be placed. In excavating for the second set of piles, a very large rock was encountered. This and other rocks were blown up by expert quarry blaster Arthur Wallis. By the end of April 1964, 30 piles had been driven, initially of 10 feet depth, but thereafter the lengths were increased according to the firmness of the ground. With intensive activity across the site, Farr's insurers were worried about public access. Some fencing was erected, but it was physically impossible to keep the public out. It was shocking to look back and see the complete absence of PPE equipment, apart from Wellington boots. It was a hazardous site, and safety relied on awareness and careful working. Now, looking at the progress of the work in more detail, refreshing my memory from scraps of surviving documents, including my works diary. Firstly, the site must be made accessible for the machinery. A temporary track was laid over the rough ground from the existing promenade. An initial trench was dug along the line of the new wall, followed by excavation to foundation depth for the first bay. This had to be in the stiff clay well below the slip plane, under the gooey, unstable soft clay. A frame was erected as a guide for the piling, which had to be driven and pitched vertically. The piles were driven in panels of 10, the end ones being driven first, with blows from the impact hammer suspended from the crane. A black varnish was applied to the steel. Within a week, in April 1964, a large mass of excavation had collapsed back into the trench, which then became flooded by rough ground swell waves. Concrete was placed behind the piles, and the decision was made to double the specified steel reinforcement in the base slab. Vertical dowel bars were set in to key in the mass concrete wall. Timber shuttering was erected for the back of the first bay of mass concrete wall, with a top chamfer where the sloping rock batter was to be. The front wave return was formed with a strong, purpose-made steel shutter, which had to be cleaned and oiled before each use. On the side end of each bay, a strong vertical timber shutter held the poured concrete. 3 shaped holes were cut into that end shutter for dowels, which were actually railway metals, recovered from the long-closed historic Merchants' Railway at Priory Corner. One half of those railway dowels was bedded in the concrete, while the protruding half was covered in bitumen to prevent it bonding to allow for movement at the joint. All the shuttering had to be firmly braced to avoid bowing or movement while the concrete was setting. Between each 15-foot bay is Flexel expansion jointing sealed with plasti-joint. The brown seen on the face of the wall here is a curing compound applied after the shuttering was struck. Counterforts comprised 6 sheet piles driven at right angles to the face, which I had increased from the specified 5. The front of the reinforced base slab was formed as capping to the front piles. In May 1964, a large amount of water was still flowing down into the works, so additional temporary drains had to be laid. Now the piling depth was increased to 15 or 20 feet where practicable. However, in places the underlying clay was so dense and hard that driving into it was impossible, even after 4,000 hammer blows. The resistance was 100%, causing the hammer to damage and bend the top of some of the piles. On the 30th of May, my diary records, drove line of piles behind the base slab to retain the bank, which is still very much on the move. This could be serious if we can't control this. This caused one reinforced base slab to crack and lift, which I instructed Farr to remove and excavate for a deeper footing. Here, a channel formed with sheet piles was laid across the wall to drain water from the bank behind. A pump is also working continuously. Once the formwork was firmly in place and accurately positioned, the concrete was mixed in the large batching plant on the existing prom. Here, operator Jeff Peaple controls the mix. It was taken to the site in a hopper. Speed was of the essence, as the concrete had to be placed within 20 minutes of the water being added. Here, Foreman David Rodd is guiding the concrete-filled hopper to Keith Ironside, who was consolidating the mix with a vibrating poker to ensure it is homogeneous and free of honeycombs. Keith did get out before the concrete set. Carefully placed in the mix were stone plums, clean, irregular limestone rocks to the specified tolerance and spacing. Plums improve the stability and strength of the concrete mass by reducing shrinkage and thermal cracking during curing. Concreting had to be continuous between joints, a day's work being completed at a joint between bays. Sample blocks of concrete were subjected to 28-day testing for compressive strength at intervals throughout. Farr's general foreman was David Rodd, and his brothers John and Les Rodd were the crane operators. I have listed the other personnel in the description. By the end of May 1964, steel sheet piles of up to 20 feet depth had been driven for a length of 120 feet from the existing promenade. 60 feet of reinforced concrete base in 20-foot sections had been laid, and 45 feet of mass concrete wall completed. The unstable land continued to cause problems throughout the building of the main wall. On the 25th of June 1964, some 100 feet of the bank slipped into the excavation. A mass 7 feet thick extending 50 feet up the bank slid down, threatening the huts above. It was potentially catastrophic. After this was cleared, I had several additional temporary land drains laid. Rough seas and spring tides flooded the excavations several times. The work was protected to some extent by the bank of excavated loose material on the beach fronting the wall. The sea gradually washed this away as planned. Despite the problems, the main wall was now being completed at the rate of some 30 feet per week. Drainage running along the back of the wall comprised a pipe and crushed stone fill. From there, weep holes were formed through the wall to allow the groundwater to escape and to relieve hydraulic pressure. The final bay at the southwest end was poured on the 20th of August 1964, 14 weeks after the first one. Taking heed of the ministry inspector, the parapet walls alongside the steps at each end were greatly increased in bulk and strength. The foundation of the southwest return end wall was constructed deep into firm clay amid the very rocky ground, and piles up to 20 feet long were driven below this. The concrete landing platform there was made thicker and deeper than specified, and altogether the end structure, the steps, parapet and return wall created a massive anchor to the overall structure. This block end was designed to prevent any outflanking, even by the most intense storm waves that can impact this most exposed corner. The end steps were formed between two massive parapet walls, both well founded on reinforced concrete bases. The space between them, under the steps, was filled with huge rocks and fines. The consultant had recommended a concrete fill, which I decided was unnecessary and too costly. Instead, we increased the reinforcement in the steps, added more ties to the side walls, and doubled the concrete thickness of the steps. The concreting of the southwest steps was completed in October 1964. A small flight of steps was created from the bottom of the main flight to give access to the rocky shore. The additional beefing up at the southwest end created two distinct and very heavy elements, the return wall and the lower steps and platform. These should have been separated with a flexible construction joint. That omission led to a crack occurring in the outer parapet wall, but stability was not affected. A deep silt pit manhole behind the end of the promenade at the top collected groundwater from the land drains. From there, a 9-inch cast iron pipe was embedded under the steps to an outlet through the bottom landing. On completion of the wave return wall, the unstable clay slope above it was dug away, and stone fill was imported to build up the bank to the required profile. The problem of consolidating a 21-degree slope was resolved by using an 8-ton roller tethered to a winch on the 19 RB dragline. I had visions of the rope snapping with disastrous consequences, but Farr's men had confidence in the method and all went well. However, later, in a different operation, on the 30th of October, a near disaster occurred when the big 19 RB dragline ran away down the bank, snapping off its jib and damaging its cab. Fortunately, the driver escaped unhurt. After compaction, large random stone blocks up to a ton were lifted in position to form the revetment. While this was primarily for protection and stabilization, I was keen to ensure that this major feature would be attractive with a rugged profile, including, if possible, some fossils. The stone blocks were surrounded by concrete and grouted with cement. In the meantime, in late 1964, the major grading of the hinterland was underway, mainly using the Drott bulldozer. I set out a grid over the entire area to give Farr's profiles to work to. A critical network of land drains of varying depth was dug over the whole area to pick up all the groundwater, which was a major cause of the landsliding. Nothing dates a picture better than a site engineer wearing a jacket and tie. No hard hat or high-vis PPE to be seen. Behind me here is the site of the main groundwater drain and the spur road. At the eastern side, the water was channeled to the the main drain, a 9-inch pipe in a deep stone-filled French drain. This was to be under the spur road leading up from the promenade. I was concerned to come across these men working in this unsupported deep trench without trench sheeting. Any risky practices were quickly resolved. A deep manhole 6, was built to give maintenance access. I was concerned that this would be susceptible to movement and cracking given the ground conditions there, as a deep crack had already opened up in the land above. So I had the spun concrete rings surrounded by strong in situ concrete, belt and braces. Water from there was discharged through an outlet in the wall onto the beach by the north end steps. Original topsoil was sparse over the Kimmeridge clay hillside, so topsoil was imported from fields off Lanehouse Rocks Road, Weymouth, where Ray Curtis was clearing land for his Channel Ferry car parks business. This was spread and graded over the hillside, leaving indigenous grass to recolonise it. Leaving the ground bare would have increased erosion. The promenade was then constructed to light carriageway specification. The outer edge was supported by a continuous curb on a reinforced concrete bed, and along the back of the prom a dwarf retaining wall of natural stone was built to keep the prom clear of any bank slippage. This was also an ideal place to have future benches for the public. Behind this was laid a continuous and stoned land drain with spurs to intercept groundwater. My 22nd birthday on the 7th of December was spent checking that work. One of the last sections to be constructed was the flight of steps at the north end. Steel piles were driven under the return parapet wall there. This had a 5-foot wide reinforced concrete base extending all the way under the steps. The high wall of the earlier sea wall was drilled to insert railway metals to key in the steps. This parapet wall was the only part of the scheme which suffered from some faulty construction. The shuttering of the lower section was struck too early, causing the wall to bow, and was probably the cause of cracking which occurred soon after. The structure itself was otherwise completely sound, but 60 years later that cracking has still not been repaired. At the base of the main northern steps we built a platform and secondary steps out sideways to give access to the beach at times when the shingle level is low. This is normally unseen under the shingle beach, and this too was founded on steel piling. The important footpath link from the spur road to Cove Cottages was on an unstable slope, so we formed a miniature retaining wall to retain its lower side, which successfully kept the path in place. Overall, Everyone involved in the construction of these works was satisfied that this corner of the coast was given as good long-term protection as possible with the available technology. All tribute to the site personnel of A.E. Farr for their expertise and diligence. One issue has been the failure of subsequent authorities over more than 60 years to do any meaningful maintenance, particularly on one section of the tow beam near the southwestern end, where exposed piles and concrete have become badly eroded. I first recorded the exposed steel there in October 1964. However, at a cost of some £93,000, the Borough Council did build a major augmentation block in 2011 to protect the lower steps and to create a better and safer access to the beach at the southwest end. This greatly helped safeguard the protruding corner. Unfortunately, this became marginally undermined as the base was not deep enough, and it didn't extend far enough along to protect the exposed and eroding piling and tow beam. On completion of the main scheme, minds turned to the upper part of Cove Cliff, which was still crumbling onto the earlier promenade. Engineer and surveyor Eric Cullen had the idea of building a structure of multi-layered tiered chalets on the face, but instead a straightforward masonry wall was the more affordable solution. My layout for this high wall included a recess at the end to accommodate a future cafe building, where eventually Quiddles came 40 years later. This was my last design job before leaving the Portland Council. The wall was constructed in 1967 and has well stood the test of time.